I don't have the archive numbers. There's sufficient information. Yeah.
It's 1505 01537. The last one is Watanabe.
Oh,
Okay, well, we're very happy, I'm very happy at least, to have Riccardo and Rattazzi with us. Riccardo and I go way back to Berkeley in the late 1980s.
even earlier.
Even earlier, yes, that's right. We've collaborated. He's much more famous than I am, and he's going to tell us about semiclassics, Goldstone bosons, and CFT data.
Okay, so let me start with a little joke about the three great steps in the development of physics associated with the names of Archimedes, Lagrange, and Feynman. These names are just signposts for the many people that stay behind these three steps. And the three steps are the discovery of statics by Archimedes. Just take a lever, just put equilibrium. Archimedes could find ways to find equilibrium points, but could not predict how things would evolve if you just move away from equilibrium. Could tell you how many people you need to move a boat, but he wouldn't be able to tell you how fast the boat would move. Then we got dynamics, and that corresponding to stationarizing, something slightly bigger than the potential is the kinetic energy minus the potential, and that's the least action principle. The action is T minus V. Okay, the integral of that. That gives you a way to study how things evolve when they are out of balance. And with the discovery of the action, this very interesting and subtle object, which from the point of view of classical mechanics is just a redundant object. If you take action, you multiply by 2, the equations of motion are the same. If you really say, oh, this object is really the crucial thing, then you can start thinking about crazier things and just get to the path integral. That's the next step. Of course, it's more than that, but this, in a sense, can be viewed as the three, if you had to epitomize in a short time, the three steps. And here, of course, you can have superposition of things. And now, what is the regime? As we know, the regime where the third lever comes in is the regime where S over H bar is small, is not very large, but you can go from one, you can go back in time depending on the physical situation where you are. Right? If you are random dynamics, but you're only looking at stationary points, Archimedes is okay. If you want to do quantum mechanics, but for some reason or by assumption, the configuration you're considering have, let's say, make it very short words, large action, then you can resort back to the methodology of Lagrange, okay, and that is the semiclassical method. Okay? So when S is much bigger than 1, you can do semiclassics. And we know very well how to do that. The path integral amounts to computing all the relevant quantities in a systematic expansion around the subatomic. And the talk of today concerns particular situations in conformal field theory where you can apply systematically semiclassical methods. So let me give you a few words about that. Okay. So in the last few years, well, in the last few decades, but in particular in the last few years, we had progress in the way to extract, to control the relevant information about conformal field theories. Conformal field theories, like in the words of my friend Slava Riccardo, are mathematical structures. Okay? And the mathematical structure is characterized by a set of data, the CFT data. The CFT data are the quantum numbers, which is to say the dimension and the spin of the operators. Okay. Well, I'm schematizing here. And any other possibly global quantum number, okay, some flavor of symmetry. So they are the quantum numbers of the operators associated to each of these quantum numbers. Let me draw all the other guys, and let me only take the dimension and the spin. So there's going to be operators like this. And well, let me write the other quantum numbers. Let me write them A. Okay, so other quantum numbers. This is the first set of data is the spectrum, which operators, in this case, primary operators exist in the theory. And the second piece of information, which you need to specify the theory, is how these operators interact. Delta, LA, 1, so here there's operator 1, operator 2, operator 3, given any three operators characterized by a set of data, or a set of quantum number, dimension, spin, and any other internal quantum number. There's one number that characterizes the 3-point function between these three operators, and that's it. Given the 3-point function for all possible operators, and given the spectrum, the theory is fixed. That's the amazing properties of conformal field theories. And in recent years, we have developed methods to unveil the relations that exist between these 3-point function coefficients and the spectrum of the operators. What I'm saying is that not all possible choices for these quantities correspond to a well-to-do theories that can exist. Okay? So there are constraints. There's a square. The space of CFTs is characterized by this data, but it's a submanifold in this space. And the whole bootstrap program is aiming at shaping this space and finding relations between this. Okay? So it says the bootstrap consists in finding constraints on the low-lying spectrum. Low-lying state operators. Low-lying means small quantum numbers. Delta, L, and any other quantum number not large. Okay. For instance, there are all this study of the three-dimensional Ising model. What they get information about is information about the dimensions and the fusion coefficient of the first 2, 3, perhaps 4 operators. Admittedly, this is an interesting set, okay? But it's truly considering this low-lying guys. You can view these low-lying operators, those for which the quantum numbers are small, as the genuinely quantum objects, because there's no large parameter there. And to be semi-classical, you need some large parameter, you need large quantum numbers. Okay? So this is a genuine quantum regime. There is, however, had progress in studying analytically. Well, I should say that most of these results here are obtained numerically. There has been progress, analytical progress, in constraining the structure of this data in the regime where essentially you have sort of a semi-classical behavior. And there are two examples of that. One is the analytic bootstrap. And that there have been papers, there are essentially two main papers on this, and then there have been follow-ups by Komarkowski and Zhifoyedov, and another paper by Kaplan, Fitzpatrick, I think stuff in Holland. And basically what these people have shown is they discover something interesting about the behavior of operator fusion. So when you have two scalar operators of dimension delta 1 and delta 2, and you consider their product, and you consider the OPE, in the OPE of these two operators, they prove that at large spin, there exist operators of dimension delta L that is given by delta 1 plus delta 2 plus 2L, sorry, plus L, minus delta, minus delta L. So where delta L is much less than 1. Which means that essentially the product of these two operators contains operators that are basically made of these two guys with derivatives. For each derivative you get one power of, you get 1 unit of spin, and you pay 1 unit of dimension, and you have essentially the naive behavior that we would expect classically, up to small quantum corrections that they could somehow control using the bootstrap. Another step, and this is what I will talk about today, was presented last year by Hellerman, Orlando, Rafford, and Watanabe, and that's a different situation. What they were able to show, modulo some, in my opinion, minor assumptions, plausible assumption, is that in any CFT, let me say here, let me just erase this. And what they're proving here, what they've taken, what they've been able to argue and prove, they have considered in any CFT, although they have applied it in the particular case of a 2 + 1 dimensional CFT, operators, the correlator operators with some large internal charge Q. Okay, so take operators with some, let's say there's a one charge in the CFT, and you consider operators where Q is much bigger than 1. Okay, say charge 100, 1,000. What they've proven is that how to compute the spectrum of these operators, and what I will, but the methodology that they introduced, okay, the methodology is based on the Lagrangian, which identifies the relevant degrees of freedom, essentially Goldstone bosons, as I will argue, allows to go beyond that, okay, and this is one of the things I would like to discuss at the end of my talk. It gives you the opportunity not only to control the spectrum, but to compute the correlators. In other words, you really have control in this limit to the data, both the spectrum and the fusion coefficient. And the way you control them compute physical quantity, compute data in a systematic one over Q expansion, where order by order in 1 over Q, you have 3 parameters, which in the description would be associated with counter terms, but at any given order in 1 over Q, you have virtually infinitely many observables, which you can compute infinitely many quantities. So you have very non-trivial predictions. Situation is exactly the same. In fact, it's truly the same as you have in low energy QCD, where the pion Lagrangian is characterized by infinitely many parameters, which are the coefficients of the local operator in an expansion of derivatives over the QCD scale, the raw mass, 1 GV. But at any finite order, if you are at sufficiently low energy, you can expand all observables in a power series in energy over raw mass, some power, and make inferences in exactly the same way. And compute infinitely many quantities of a finite number of parameters, of 3 parameters at any given order, at any given precision you want to reach, and then you have. So this idea of Hellerman really makes it's an interesting opportunity for practitioners of model building and effective Lagrangians, because it sets a formal mathematical physics question, in other words, what can you say about the data of the CFT, in a framework which is what model builders like me have been playing all their life. Okay? So rather than building some model that may or may not exist, okay, you use these methodologies to constrain conformal field theories that definitely exist. Like in the case of Hellerman, they studied, and I will show it again later, they studied the simplest theory in 2+1 dimension with, actually in 3 dimension. Yes, it's liquid helium at its critical point. It's a conformal field theory with one global charge. So you can really study that theory using this methodology. Okay, so let me give you I now want to give you a. Let's see. I already spent 20 minutes with the introduction. 15. So the essential idea is that such operators with large charge are associated with states, but the operator-state correspondence, and these states are states with large charge. Okay, and path integral with the path integral around the states is going to be very similar. In fact, it's going to coincide with the path integral around configurations of the quantum field theory, where you have a large charge density. These are precisely the configurations that you have in condensed matter, like when you have a superfluid. Okay? And condensed matter states of any quantum field theory can be viewed as, in particular, as particular configurations that realize nonlinear space-time symmetries. And in this setup, the resulting Goldstone boson that associated with this nonlinear realization of the symmetry are precisely the hydrodynamic modes of the system, of this condensed matter phase. Now, this is the situation in field theory, but before going to field theory, let me give you a nice and simple analogy which epitomizes, contains all the basic idea. And this is consists of the study of the fast spinning rotor. Okay? That is to say, just a particle on the sphere characterized by 2 coordinates θ and phi, and an action I over 2 theta dot square. Okay, so this is just, so if you interpret this as a particle, this I is the moment of inertia, is the mass times the energy square. And so, this is a system that contains all the ingredients. In fact, if I were able in this hour to just talk about this, I think it would be enough to then make analogy and explain what this idea of Hellerman does and how to generalize and how to use it. Okay? Because this system contains, first of all, it's a sigma model. It's already a coset. The rigid rotor corresponds to the coset SO3 over SO2 in 1.0 field theory. We only have time, okay? And that's, and if the point is at rest, of course quantum mechanically this doesn't make sense, but let's say classically, if the point is at rest, that is the pattern of symmetry breaking. On the other hand, if the point is moving, let's say is moving fast around the equator, then the velocity is breaking the residual symmetry. So what you really have, you have a coset where SO3 is completely broken. And not only is the coset, the global symmetry SO3 completely broken, but also time translation invariance is broken because the guy is at a different point at different times. However, so let's say moving theta and phi, let's say theta is pi over 2 and the equator and phi dot equals some omega t. Okay, imagine like this. Now, in this situation, SO3 is broken to nothing, time translation is broken. However, there is a linear combination of time translations and rotation that is left unbroken. Okay, this particle is rotating at constant speed around the equator. If you do a shift, if you do a rotation along the third direction, you shift phi. But you can compensate that by time translation. So there is a linear combination of these two symmetries that is unbroken. So you have a pattern of symmetry breaking, which is SO3 times time translation, that goes down to an effective time translation. Okay. It's essentially the Hamiltonian minus omega times J3. Okay. So I will explain this better in a moment. Okay. So this is exactly all the ingredients that enter in the methodology of Hellerman. So let me explain it better. So let's consider this system, and let's say I want to extract information about its spectrum, and in the regime of very large angular momentum in one direction. Okay. So angular momentum is J3 in the third direction is I sin squared theta times phi dot, and it is the variable that is canonically conjugated with phi. Okay? They are, from the Hamiltonian point of view, they are the canonically conjugated variables. Okay? And I want to study this system semiclassically in the regime where J3 equal m is much bigger than 1. Now, as you know from quantum mechanics, that's precisely the regime where you can apply semiclassical methods. Okay? And in fact, you can check it while doing it using path integral, but that's the regime you want to go. And of course, it seems stupid to apply semiclassical method to the system that is exactly solvable. We know that it can be exactly solved. And the spectrum is organized in spherical harmonics, okay, with energy given simply by L plus 1 over 2I. Right? Then you can exactly solve it. But what I want to show is how this result is derived in the semiclassical approximation, and how this emerges, and what is the pattern of symmetry breaking associated with that. And once that is understood, it should become, it's just a simple translation to apply the same ideas to CFTs. So let me discuss this. Okay? So perhaps I should erase this. So the main tool to progress in this game is to consider the path integral. So states, in other words, states are characterized by the two coordinates, but I can also consider states with fixed value of angular momentum in the third direction. And I do that by projecting. Essentially, I take the state with fixed value of 25 and I fold in by e to the n phi and integral of phi to phi. This is the state with e. M is just momentum in the phi coordinate. Okay, that's just the usual quantum mechanics. Now you project the states which have fixed angular momentum in the third direction and not fixed theta. And now what I want to consider the path integral between states of this type, which have this given large eventual value of angular momentum, some final theta f, consider e to the minus I h t final minus t initial. Let me do it Euclidean path integral. Okay, so that this is Newtonian is theta initial. Now, this is the essence of, this is the basis of all my derivation. Okay? This path integral is written as an integral of I e to the minus integral of L plus I and phi dot. You can easily see where this is coming from. The ordinary path integral does not have this. When you go from some initial value of theta, psi initial, theta initial, phi final, theta final, you have just this. Okay. However, if you integrate over the initial, the phi initial, the phi final, folding in by this phase factor, you are projecting on state with definite m. And now the integral over time of phi dot is equal to phi final minus phi initial. This object here gives you precisely the projector of the final initial state with the angular momentum m. Right? And when you do that integral, that means that this has been integrated over. Okay, I could just imagine this integral here to be inside of this, and all I did is a path integral with fixed initial value of theta, theta initial, theta final. Okay. Now, when I do a path integral of this type, okay, see, if I don't specify further if I don't project further theta, I have not specified what the total J is, okay? The total L is. Okay. These states could in turn be decomposed in states with fixed L, okay? But I don't. I just leave L as not specified. So this integral here will decompose, or if you want this sum here, will decompose into, you can write it as, I could decompose the state into states with the fixed L, okay? The total angular momentum. And those are eigenstates of the Hamiltonian, and each of those, when you do this decomposition, this object here will decompose as a sum of exponentials, And it's clear that when time goes to infinity, when these guys are very separated, the leading contribution will be from the state of lowest energy, which is the state which has the smallest possible L compatible with M. So T final minus T initial, in this case we know you're dominated by the so-called ground state, which is the state of lowest energy and fixed value of J3, okay? Which I call E0 of M. Now, in this particular case, we know what this energy is, okay? Because the state of lowest energy with fixed M is the state we know is the state where L is equal to M, okay? And E, therefore, is equal to M plus 1 over 2R. But imagine I don't know, okay? And that's precisely what will be the situation in the conformal field theory we'll consider. Then we can imagine to do the computation and see what information we extract. Now, it turns out that when M is much, much bigger than 1, in this interval you have a big number, okay? And you're precisely in the situation where you can do this integral by the semiclassical method, okay? In other words, you find the stationary trajectory and then you expand around. So let me give you the basic story here, how it works. Let me just erase this. Do you have any questions about this? I may just tell you stupid things, too simple. Now, in a semiclassical method, you have to find the stationary trajectory. So what you, it's just a simple detail. The stationary trajectory, normally, of course, this is a total derivative, so the only thing that matters about this M here is precisely the boundary term, the boundary condition. So the boundary condition will fix the stationary solution. The stationary solution as, if you choose, for instance, theta initial equal theta final equal pi over 2, just put it at the equator. I will say in a moment, this is not crucial. I could have chosen any different value, I would have gotten the same result, as I will explain in a moment. And phi is equal minus I m over I t plus phi 0. That's integration constant. So that's the general stationary solution. Let me tell you something very simple. If I had chosen different thetas, then the stationary solution would have had theta time dependent, but theta would have gone exponentially fast towards this thing here. It's understandable. The configuration of minimal energy with fixed angular momentum is rotation on the equator. You could have rotations in a different direction, but to get the same m along this direction, you should rotate faster and would have higher energy, and it would be exponentially suppressed when you send it to infinity. The dependence on t, of course, is imaginary because we are in the Euclidean time. If you go back to Minkowski time, then it's ordinary. Of course, this is a stationary trajectory, and like in all respectable saddle pony methods, it could lie in the complex plane. As I said, this trajectory breaks the original symmetry down to a subgroup, okay? Breaks SO3 times, let me call it H, time translation. Okay, these are the two symmetries of my problem, okay? There's spherical symmetry SO3 and the time translation symmetry. These are the symmetry of the problem. And this solution breaks the symmetry down to a an effective time translation H prime, which is equal to H minus mu cubed, where mu and mi. Where mi, well, if you interpret, let me call it mu, where the role of the chemical potential is played by the velocity of rotation. Here there are the two inventors of Bose condensate. This is just a simple example of that, right? It's just spontaneous breaking of time translation invariance by Goldstone boson having a linear dependence in time. You may be worried by this I. Just go back to Minkowski, that's the usual thing. Notice, which I have erased as it's here, notice that, however, even though you have a pattern of symmetry breaking, you're at finite volume, so there's no spontaneous symmetry breaking. So for instance, when you compute correlators among the state M of objects with definite quantum number, let's say M1, phi 1, e to the I n phi n, the e to the I mn phi tn are just local operators, okay, with a given charge m under rotation in the third direction. This is a way of writing an operator with charge mn, okay. Well, this integral here, even though your solutions spontaneously break the symmetry, at the end of the day you also have to integrate on the zero mode, which in infinite volume theory would decouple. And when you integrate over this, symmetry is restored. This is not zero, only is proportional to delta m1 plus m2 plus mn. So the parlance of symmetry breaking is correct. Okay? You have a semiclassical trajectory that breaks the symmetry, but you're doing quantum mechanics. Okay, so the symmetry is quantum mechanically realized. Although when you do the computation using the path integral around the semiclassical trajectory, it's as if you have symmetry breaking, and the excitations of this phi is a Goldstone boson in all the ways. The only thing is that at the end of the day you have to integrate over the zero mode, and this restores formally the symmetry. But in all intermediate stages of computation, we are on the grounds of Goldstone bosons. So in fact, this is a pattern of symmetry breaking of space-time symmetries, time translation. You would expect in general how many Goldstone bosons? John? Eh? 2. Well, you 1 in the end. Well, in general 3, because you broke an SO3, and then so 1 can always be eliminated by the so-called inverse hit. In fact, I didn't even have it to start with. Another one has mass, and as I will say in a moment. And another one is genuine Goldstone boson. So this theta corresponds to a massive Goldstone boson, and this is the genuine one. In fact, let me. So let me tell you, if you consider it's interesting to consider now, so this is the solution, okay, and the class, the Lagrangian, the integral of the Lagrangian, if you want, the integral of S plus phi dot m, of L plus phi dot m, there's going to be some classical action, plus quadratic perturbation, plus cubic perturbations, and so on, right? So let me write my variables. Theta is the theta classical, which is pi half, plus some perturbation xi, this is the quantum fluctuation, and phi as my classical solution phi here, okay, plus a perturbation. Okay? Now, if you compute the action around this solution, you find that the action is given by m squared over 2i times time final minus time initial. And of course, in this sense, this object here is interpreted as the classical contribution to the energy of the state of lowest energy. And the quadratic action has the form I over 2 psi dot square plus eta dot square plus m over I square psi square. So what you have is that theta, this psi, the excitation of theta is a harmonic oscillator with frequency equal given m over I, and this m over I is what plays precisely the role of chemical potential. So this is a well-known fact that when you have this pattern of breakdown of that mixes internal and space-time symmetries, not all the Goldstones are massless, but there are always Goldstones that have a gap, and the gap is controlled by the chemical potential. And on the other hand, eta is a genuine massless Goldstone. And now, using this perturbation terms, you can develop a loop expansion and compute higher and higher order correction to the ground state energy. And what you find is that, so you have these results. So the 3 level E0, the various contribution to E0, okay, E0. Okay, these are the contribution to E0 of M. So you have at the 3 level, you have a contribution that goes like m squared over 2I. We have checked all higher loops. And now the expansion in loops is the loop expansion is equal to the expansion in 1 over n. In the inverse of the angular momentum. Okay? So at one loop, you should get terms that go like m to the first power. So 3 level is m to the second power. At one loop, you get terms that go like m to the first power. And indeed, the leading term is coming precisely from the ground state energy of this harmonic oscillator. And that ground state energy is precisely given by 1/2 omega psi, which is precisely m over 2I. There's also a constant associated with the UV divergence, but it is independent of m, and we don't care. It has to do with the regularization of the path. Notice the interesting thing that 3 level in one loop, when added together, already saturate the exact result. Is equal to m plus 1 over 2I plus constant. The constant we don't care very much, it's just a constant, but we already saturated the result. It means that all the higher orders should non-trivially cancel. Okay. And we have checked that. If you go to 2 loops, you should get m to the 0. M to the 0 is a constant. We do get a constant at 2 loops, but again, it doesn't change. It goes along with the fact that there is a divergence in the path integral. So this Lagrangian has one divergence, the cosmological constant, and that's it. And you can normalize it to the value you want, in particular 0. What is really non-trivial is what happens at 3 loops. Because there you have m to the minus 1 in principle. Okay? And if you compute diagrams, you really have contribution to go like m to the minus 1. And it's very, very non-trivial how all these diagrams cancel. Okay, so you get 0. In fact, to do the computation, we were confused for a while about this, because to do the computation we were using dimensional regularization. We were extending this to 1 plus epsilon. And 1 dimension is a very special dimension. You have a sort of anomaly. In 1 dimension, the term d psi square, in other words, d psi is a perfect square. It is equal to psi dot square. But that is not the case in higher dimension. It's not a perfect square. And that's the sort of anomaly that singles out 1 dimension. And when you do the analytic continuation to 1 plus epsilon, you have to be very careful. In fact, it's precisely due to this that there are evanescent terms that allow this cancellation. I'm still not happy about the fact that I don't see it right away in this methodology. Of course, I know the exact result, but it's very weird. Anyway,
What sort of diagrams are you actually computing? You just give an example.
the diagrams we computed, there's, for instance, this diagram here, this is psi, and this is one diagram. These are etas, okay? Diagram like this, and there are diagrams of other type. Right, this is an example of a diagram. Anyway, this is just to show that what you can do. Now, you can imagine extending this to the case where you have just let me just say it in words. You can apply the same methodology. Now, of course, this is just so far I've given a course in quantum mechanics, in medium quantum mechanics. But after this is clear, then the translation to CFT is automatic. Let me say something else. You can, of course, here we knew what the theory was to start with, but we could apply the same methodology rather than studying the rigid rotor to studying an arbitrary particle, a particle in an arbitrary spherical symmetric potential. If the spherical symmetric potential grows sufficiently fast at infinity, when you spin it very fast, the particle will go away from the origin, so the semiclassical trajectories will be dominated by trajectories that are away from the origin, which de facto spontaneously break the symmetry in the following way. Okay? So the same pattern of symmetry breaking is also expected regardless of the fact that you have a rigid rotor. So it's the general pattern that describes the semiclassical limit fast spinning particle in a radial potential. So you see we have a general thing. However, you have to be careful about what is universal in these cases. And what it turns out is that unless the potential is very, very steep, in other words, unless there is a very big parameter in the potential, the radial mode and the theta mode have comparable mass. In other words, you do have a description in terms of a sigma model, this spherical sigma model, but the radial modes, which are non-universal, have the same gap as one of the Goldstones. So if you want to have a complete description, a consistent description, if you want to have all the Goldstones, you also have to add the non-universal modes, or you have to give up some of the Goldstones. In particular, you have to give up this Goldstone psi, you only left with eta. And the dynamics of eta is not very exciting. It's very trivial, okay? You don't get much information. Now, it turns out, however, in the case I will consider in a moment, you have exactly the same situation. However, the dynamics of eta is not trivial, because we will be in quantum field theory. So let me now try to translate this to quantum field theory, okay, to CFTs. By the way, here I could compute correlators precisely this way, by mapping expression with Goldstone bosons into any operator with a given charge under rotations. Now I can, after this long introduction, and probably not convincing, I will just outline what one would like to do in conformal field theory. So what is the goal? The goal, now we are in CFT. What I want to consider is correlators where there is inserted at the origin x0 going to 0 some operator O with some large value of internal charge. Okay. Let's say before we had m theta. Okay, these were the states were characterized by J3 and theta. By the way, I could have exchanged J theta, I could have expanded any state characterized by M and theta by expanding theta in Legendre polynomial with L bigger or equal than M. Okay? So I could go to a discrete set of states, but anyway, there's some additional quantum numbers. Now what I want to do, I want to consider operators characterized by some large internal U1 charge, and whatever other quantum number you could have. Now the interesting thing, the crucial thing in this correlation, remember here I have talking about states, here I'm talking about operators, is that in CFT, there is an operator-state correspondence. For every operator, you can associate a state. And that is done by the so-called radial quantization. Let me illustrate just briefly how it works, okay? So what I want to consider is correlators where I have an operator with charge Q and whatever other quantum numbers inserted at the origin. And then there is another operator with the opposite charge, minus Q, and some other quantum numbers, inserted at x infinity where this is going to infinity. Okay. So essentially, I insert an operator of charge Q in the origin, and an operator of charge minus Q at infinity. Okay. Far away. On the plane. Okay. Now, it is a remarkable property of conformal field theories that you can view the theory on the plane as a theory on the cylinder, okay, and preserving the symmetries of the theory. Okay? You can map the coordinates on the plane, x, to coordinates on the cylinder in the following way. So this is RD, the d-dimensional plane. My field theory is there, it's a field theory. And then I map each point into a unit vector on S d minus 1 times e to the minus times r, the radius of the sphere, e to the minus tau time over r. So now tau, so this is parameterized by n and this is parameterized by tau. So this is a cylinder, okay? And so the origin, x0 corresponds to tau 0 going to minus infinity. The origin corresponds to minus infinite time, and infinite radius corresponds to tau going to infinity. Okay, so the origin is the far past, and infinity is the far future. This is the radial computation. And in this mapping, an operator inserted at the origin corresponds to a state. Okay? To a state in the far past with the same quantum numbers of the operator here, a cat, while a state, an operator inserted at infinite radius corresponds to a bra minus q inserted at infinity here. Okay. And so, if I now insert operators everywhere else, this situation will map into, say, if I insert operators here, everything will map to the following thing, that is minus qa in the future, all other operators O1, x1, On, xn, qa in the past. So now these correlators, therefore, are similar to what I had in the rigid rotor case. Okay, remember, this is precisely what we had before. We were computing using particular correlators between states with some large charge and whatever other quantum numbers. Okay, this A plays the role of the thetas, if you want, and this Q plays the role of M. And now, when we consider the path integral with fixed charge, it's going to be exactly the same as before. When time goes to infinity, when this cylinder goes to infinitely long, the dominant state that will dominate the state will dominate the path integral. This is the state of lowest energy. So when tau infinity minus tau 0, the corresponding time of the two insertions here, go to infinity, the path integral is dominated by some ground state, which I call Q, which is the state of minimal energy at fixed value of Q. Okay. Now, what is energy here? Energy on the cylinder is just the dimension of the corresponding operator times 1 over r. So up to 1 over r, a trivial coefficient, energy and dimension are the same thing. Okay? So say it in terms of operator, when I send this time separation to infinity, what dominates here is the insertion at infinity, plus or minus infinity, of the operator, or sorry, the insertion at the origin of the operator with charge q and lowest dimension. Okay? So the situation is exactly the same as so it can be treated exactly the same way. Now, I expect that when this q is very large, essentially the path integral will be dominated by configuration, like in the case of the particle in the potential, that are very far away from the origin of coordinate space. And here, of course, here one is speculating, okay? And the leading trajectory will be therefore dominated, described by a set of Goldstone bosons, the excitation around this trajectory. So boson whose properties we can study in the systematic way. That's the idea. Okay? So it's just the translation of the rigid rotor to the situation. And it can even be generalized. So here I'm considering A1. I can even consider the case where these Qs are the Cartan charges of some arbitrary non-abelian group. Okay? That can be generalized. And let me...
Can I ask a question?
Yes.
When you say large, presumably it means large compared to
the minimum quantum.
The minimum, right. So my question is, does the existence of those operators with small charge enter anywhere into your derivation? It should somehow enter as a justification for some classes.
So you're asking me, sorry, can you repeat the question?
Well, the intuition is that if the smallest charge has charge 1,000 and you're doing charge 1,000, then you're not going to have a good...
No. Of course, what I'm doing here, very good question. What I'm doing here is that whatever that limit, that lowest value is, I'm asymptotic. So I'm really taking the limit where Q is going to infinity. So eventually I will be there. So it's not, I don't have an absolute reference value. I'm writing asymptotic formula. And nobody tells me at what value of Q this will start working. You're right. Now, physically, I would expect that in a theory where there is a certain, where the fundamental degrees of, where there is some operators of charge 3 in some units, then the thing will start working when the charge is not bigger than 3 in that sense. But that's, you see, the unit of charge, if this is an abelian group, it's arbitrary. The non-abelian case is less arbitrary. Does this more or less address your question? Now, I'll give you an example. So what I'm saying is that, let me just give you the slogan here. Q much bigger than 1 tells you that the path integral, whatever it is, e to the minus s, is dominated by some classical configuration, okay, that corresponds to the state of minimal charge. Very much like in the case of the rigid rotor, the path integral was dominated by this phi spinning on the equator, and that phi fast spinning on the equator corresponded to the state of angular momentum equal to m, exactly corresponding to the state of total angular momentum m, and J3 equal m, therefore just oriented that way. So the configuration I find should correspond to this ground state. Now, this configuration for the theory on the cylinder, okay, corresponds to a configuration with charge density rho that goes like the total charge divided by the volume of the sphere, okay, which goes like r to the d minus 1. Okay, that's clear. Now you see, the crucial thing is that you can view a conformal field theory on the plane as a conformal field theory when you have compactified d minus 1 of your dimension on the sphere and only time is non-compact. So a state of total charge q on the cylinder corresponds to a state in the conformal theory with charge density that is much, much bigger than the ordinary unit of density, which is 1 over r into minus 1. If you want, 1 over r on the cylinder is the mass of the Kaluza-Klein modes. Okay, so this charge density is as dimension energy to the d minus 1. Okay, and is much, much bigger than the natural unit that, for instance, would be the Kaluza-Klein mass to the d minus 1. Okay, so this quantity here, again, is what will turn out to be the chemical potential to the d minus 1. Okay? What you essentially are doing, you're considering the theory in a configuration where the chemical potential is much, much bigger than the other dimension for quantity, which is 1 over the volume. So essentially, you're in a situation where you have two scales. You have an infrared scale that is the volume of your space, and there's an intrinsic ultraviolet scale that has to do with the density of your configuration, density of charge. So essentially, this configuration is a high density condensed matter phase. Okay. And there are various options for how to realize in condensed matter a configuration of fixed charge density. Let me just tell you two, and then I'll assume it's one of the two. My knowledge of condensed matter is not good enough to imagine others, but there may be others. But let me give you the two. So one configuration to achieve this is a superfluid. Okay, it's like liquid helium. Okay, high charge density. You have Bosons condensation. Okay, and you have a given class. This corresponds to a specific pattern of symmetry breaking in space-time symmetry, which I will give you in a moment. Another option is a Fermi liquid. These I don't know what to do with. Okay, these I'm not sure I can describe. And all that I will derive is assuming this. It's a superfluid. By the way, the rigid rotor I described before is precisely of this class. It's purely bosonic system. There may be interesting systems that are in this class, but I think it's a discrete choice. Okay. By the way, and if you don't have fermionic degrees of freedom, well, you're going to be this. But this is the step where you make an assumption. This is the only step where you make an assumption. Everything once you buy this, then everything is systematic. So essentially the question is, that's the basic question. Okay. And I will argue that the simplest thing is this. Now, very quickly, finding the condensed matter phase corresponds to asking which pattern of symmetry breaking. For instance, superfluid is precisely that pattern where you have an effective time translation that is left unbroken that corresponds to a linear combination of the original Hamiltonian and Newtonian charge. In the case of Fermi liquids, that's not the case. You have a different pattern. And in fact, I have written 2 years ago a paper with De Collis, Piazza, and Penco characterizing general phases of condensed matter in terms of symmetry breaking, and we don't know how to fit Fermi liquids in this specification. It's an open question, and we're very happy to receive push on that. Anyway, on the other hand, for all the bosonic cases, we have a classification. And in this particular case, what do we expect it to be? Well, let me tell you. What is the symmetry of this configuration? Well, the symmetry will have to be, certainly, we will have the symmetry of the boundary conditions, okay? You cannot have more symmetry than the boundary condition. On the boundary condition, there is the insertion of one operator at the origin and one operator at infinity. So, inserting operator at the origin, it certainly breaks translations, okay? Because x0 translates. So, the total translation operator of the conformal theory on the plane will have to be broken. What about the point at infinity? The point at infinity can be better parameterized by doing an inversion mapping, okay? Where 1 over x at infinity becomes the origin. And there, when you do this inversion, you discover the point at infinity is shifted by conformal transformation. If you want, essentially, translation and conformal transformation are conjugated to each other. P is what shifts the point at the origin, and K is what shifts the point at infinity. So they both break. Then, if you assume that the ground state at fixed charge is a scalar, which is actually, you can actually go back and in hindsight prove it, okay? Then if this is a scalar, then rotations, okay, in the plane are unbroken. That is to say, you have SO d minus 1 unbroken. SO d unbroken. And there remains just two symmetry to decide which fate they're going to have. It's Q, the original internal charge, and dilations. Okay? And the assumption that corresponds to the statement that this is a superfluid is that these two guys are spontaneously brought into a diagonal subgroup where the true generator of dilatations, remember, dilatations on the plane are going to be time translations on the cylinder. Okay? So d prime is going to be the original dilatations minus mu q. That corresponds to the system. That, if you want, this is an assumption. But again, it's exactly what we got for the rigid rotor. It's one class. It's one fixed class, and we just assume we are in the class, and we draw consequences. So essentially, the hypothesis is that, I think I'm basically out of time, right? Okay. So essentially what you have is SO d plus 1 times Q is broken down to SO d rotations on the sphere times effective time translations. Okay? This is the hypothesis. Okay? And once you make this hypothesis, everything follows. Okay? This hypothesis may not be true, but it's a question of yes or no. Okay? It's not that it's only approximately true or not. It's either true or not true. And theories that are bosonic will be in this class. Okay? So this, if you are in this pattern, then the solution has a specific part of symmetry breaking. So excitations around the leading trajectory are just the Goldstone bosons. Associated with the symmetry breaking. Okay? And the Lagrangian is going to be written precisely with the rule by which we have the Lagrangian for Goldstone bosons. It's going to be a systematic derivative expansion, derivative, and all quantities will be computed in this setup. Now, I have to, let me see if I have to wrap up. In fact, you can generalize this to any arbitrary internal symmetry group here, and you will have that D prime is given to D minus generically a linear combination of all the Cartan generators. Okay? And as again, for any given group here, you have a specific CCWZ construction. So for any G, find the CCWZ construction. Okay? Alan Coleman does the view. Okay? And then you can write them on general. And this is what we did. Okay? This is pretty boring, and it probably would have taken 3 hours to explain just this. So this we will not discuss. Okay? But now you can systematically do all that you want. So we consider various groups. You consider U1, U1 cross U1, SO3. Okay? And we did computations similar to the ones, in fact, we did it. The simplest case U1 was already studied by Hellerman and collaborators, but we generalized it. And the computation has exactly the same flavor of the computation of the rigid rotor. Okay, let me give you the example. So let me give you the simplest example. Simplest example is given by G equal U1, and I consider D equal 3, okay, corresponding to a CFT3. This is precisely the case of liquid helium at its critical point. Okay, so this is a CFT that is the U1 model in 3 dimensions. This is a CFT that exists. Okay, and in this case, the effective Lagrangian, okay, L has the following form: C1, let me say C1 over 6. So there is one. So in this case, one Goldstone boson. There's just one. Okay. Although you have breaking a zillion of symmetries, okay, it's a space-time symmetry. You have just one Goldstone, which is called psi. And the Lagrangian has the form C. The action. Okay. The Lagrangian has the form C1 over 6 deep psi to the 3, where deep psi is the square root of deep psi to deep psi. Okay. Then, so this is a term, as you see right away, the theory is conformal in 3 dimensions, it has 3 derivatives, okay? But it's very non-analytic because this guy here, there's a square root, right? Then there are terms like, there's a C2 term that starts with, let me write it better. Okay. You have a term that starts with deep psi, and then there is the Ricci curvature on the sphere. In fact, one level of difficulty here is that you are doing sigma models on curved spaces, curved space-times. Okay? And plus a term that is 2, this is completely fixed by the symmetry, gradient deep psi, mu, gradient mu, deep psi, divided by deep psi. That's higher orders. Notice that here you can count derivative. This is 3 derivatives acting on psi. This is 1 derivative acting on psi, and 1 over r squared, that's the curvature. Okay? And similar. Okay, so, and you go on and on, you have less and less derivatives. Now, to fix the charge, you turn the path integral into a path integral of e to the minus integral of L plus I Q psi dot. You see, psi is the canonical conjugated variable to Q. Okay? And exactly like in the case of the rigid rotor, to fix the total charge, you just have to add this term to the path integral. And now we just crank the machine. We find the classical solution, expand, do exactly like in the case of the rigid rotor. The interesting thing is that the solution, psi classical, is going to go like I minus I mu t, okay, plus some 0 mode, very much like in the case of the rigid rotor, and mu mu square, sorry, it's Q over the volume. So this is the volume, and what you have is that mu square r square is equal to Q. That's the crucial equation. You have that this chemical potential goes like square root of Q over R. It is much bigger than 1 over R. And this chemical potential is precisely what controls the derivative expansion. You see, this guy here, now when you write it this way, this guy here goes like mu cube. This guy here goes like mu 1 over R squared, and so on and so forth. So the derivative expansion is an expansion, derivative expansion, okay? Derivative expansion is expansion in derivative expansion is an expansion in is an expansion in derivatives over mu squared. So the expansion in 1 over r squared, if you are at the radius of the sphere, is called expansion in 1 over q. So the derivative expansion is expansion in powers of charge. It's exactly like in the case of the rigid rotor, and then precisely like for the pi Lagrangian, order by order in if you want to achieve a certain precision in Q, you expand in inverse powers of Q. And give a simple example of this. You can compute, for instance, the ground state energy. So which corresponds to the dimension of the operator with lowest dimension with fixed charge Q. Okay? And you find the following result. Okay? So you have this given Lagrangian. There are the classical contribution and the quantum contribution, like in the case of the rigid rotor. And the final result is the following form: 2/3 in the 3/2 over pi C1 plus pi C2 Q the 2 pi C1 plus order Q to the minus 1. So you get, see, it goes like Q to the 3/2, square root of Q, it's term and term in expansion 1 over Q. Of course, these guys are all input parameter. Okay? So they cannot be predicted. They're like the analog of the moment of inertia in the case of the rigid rotor. It's an input parameter. However, there are also contributions that are totally independent of the input parameters. In this particular case, there is a contribution to this energy, which is essentially the Casimir energy, which is the ground state energy on the sphere, and that is just given by a number. Okay, the number is completely fixed. Just the Casimir energy of the Goldstone boson on the sphere. Okay. So that's an example of a prediction of that. Okay. So you get that the linear asymptotic behavior of the dimension of these large charge operators goes like the power of Q to the 3/2 times an overall coefficient that depends, first of all, on the normalization of your charge. Marcus, this is what you were asking. You see here. In your given model, will tell you what the C's are, and will tell you how fast this expansion goes. This is model dependent. However, the subleading terms are fixed, okay, and others. Now, this per se is not too remarkable. Oh, here's this tiny little thing here in predictability. But in fact, there is more, because now when you expand the Lagrangian around the solution, okay, there's the classical, plus there is the quadratic, plus there is the cubic. And in particular, if you look at the quadratic will have a certain Fock space, because here there is 1/2 psi dot square minus 1/2 gradient of psi square. Let me pi. This is pi. This is the excitation of psi. Psi is equal minus I mu t plus the excitation pi. The excitation has a well-defined quadratic term plus the interaction terms. Okay. Notice this factor 1/2. This factor 1/2 would be 1 over d minus 1. In fact, 1 over 1/2 in 3b goes 1 over d minus 1 in a dimension. For instance, in 4 dimensions, this would be 1/3. And this is the well-known speed of sound of hydrodynamic modes in the scalar invariant theory. Okay, like the speed of hydrodynamic excitation of QCD at very high temperature are 1/3 plus correction order alpha. The 1/3 corresponds to the fact that QCD at very large temperature is conformally invariant up to effects of the beta function. Okay, so that's precisely the same situation, and this gives the Fock states of this, okay, pi Fock space is made of excitations, okay, characterized by quantum number L of m, is just fixed angular momentum states of a scalar on the sphere. They are characterized by L and m. These have nothing to do with the rigid rotor element. This is simply because I'm working in 2 plus 1 dimension, and we are on the 3-dimensional cylinder, so it's a sphere times r. So momentum on the sphere is just L and m. And now you can compute the corresponding frequency associated with each of these modes. The frequency is equal to L Lm, L plus 1, square root over 2. Okay? It's coming here, right? There's 1/2 here, it's coming like this. Okay? And then, which means that when I act, so this corresponds to creation and destruction operators, Lm, A, Lm. So the action of these operators on the ground state generates states with spin, okay? And these states with spin are other operators. Their state, they correspond to operators, and they're going to have different dimensions because they have different energy. So delta Lm is going to be delta 0 Q plus sum over Lm, depending, so delta of any state, of how many quanta you have in each level. Okay? So this is really remarkable. This gives you the whole spectrum around this ground state. And some of these operators here are descendants of the original one. So they are trivial. And this corresponds to the action with L equal 1. Notice that when L is 1, L plus 1, 1 plus 1, 2, 2 over 2, 1, 1, 1. So L equal 1, omega 1 is equal to 1. It means that you increase the dimension by 1. That's precisely acting with derivatives. These are the descendants. But all the others are new primaries. L bigger than 1. And these primary descendants all come in the same package because of locality in this description of the sphere. Okay. And this is really remarkable. Now, let me just tell you the last two things and then I'll let you go because I don't want to take too much of your time. But the thing I'm going to say now are more interesting, at least to me. They find them very remarkable. You can extend this, for instance, to the case of 2U1s. There are models with 2U1s. And what you find is that apparently this nice universality is lost because in the case of 2U1, again, you have two Goldstone bosons. One has a dispersion relation which is fixed by this, which is precisely this form. But another, okay, in the case of U1 cross U1, okay, another, so you have two Goldstones. And one has omega Lm equal L plus 1 over 2. And another, so let me call this the plus mode, and there is a minus mode which has an arbitrary velocity which depends on the ratio of charges, Q1 over Q2, okay, times L plus 1 over 2, L over 2. And this is just the speed of sound of this other mode that is Model dependent depends on the charge. And this quantity enters everywhere, okay? And this is, it changes when the charge is changed, and in different direction in charge space you may even have singularities, because you could even have partial restoration of the symmetry. But generically it's just a function, and so you don't have the same prediction for the ground state I had before, because there is this function. But again, this function enters in the construction of the states of higher spin descendants, in particular the new primers. So there's going to be a whole set of new primers generated by this. Last thing, and this is what is one of the main novelties of our paper, is very much like in QCD. Let me just, it's 1 minute. In QCD, so this concerns the computation of correlators, endpoint functions. Okay? So the idea is the following. In QCD, given any operator, let's say psi bar psi, in the UV theory, in the IR theory, you write it as e to the I pi t times some matching coefficient that you don't know, and then you can compute order by order some derivative expansion. Okay? Here it's exactly the same thing. You have some operator, given some operator O, with some dimension delta, with some charge Q, and some other quantum number, let me write it A, these you can match to an expression which is fixed by the Hellerman-West-Domino construction that is purely written in terms of Goldstone bosons and their derivatives. And of course there's going to be a derivative expansion, very much like here, when you match. Like in any matching, you have a derivative expansion, but you have a leading. And now, so you can do this matching for all operators you want. For instance, the easiest thing is to do the matching for conserved current. We know how to do it in QCD. In QCD, we match the conserved current like the left-right currents, the Newton tensor, in the UV to their expression in terms of pions. It's totally fixed because it's a symmetry. There's no uncertainty. It's precisely the conserved currents of the low-energy effective Lagrangian. Once you have the effective Lagrangian, you have the conserved current. So here, for instance, we have, in the case of the U1, there is a J mu, and this can be matched must be matched to the derivative of the actual respect to the psi. So we can compute correlators of current absorption. And similarly, however, for some reason, one thing which is nice to compute is the correlator of scalar primaries, with a certain charge and a certain dimension. So this scalar primary, it's an easy thing to guess what it will be, where it has to have dimension delta, so the leading order will be just delta psi to delta. Must have charge q, so you have to fold in e to the q psi. That's, of course, it's going to be also higher derivative. Some coefficient plus higher derivative. That's like with the pions. Okay? The matrix element of the pion, you always have higher derivative over m rho 3, right? And here you can do the same. And now with this matching, if delta and q are small, you can compute the insertion q O delta 1 q1 O delta n qn as a small perturbation of path integral. And this we have done. In particular, what you can compute, you can compute the three-point function. And you find something interesting, so you can compute the three-point function. You find, for instance, that there's a universality scaling of three-point functions. The three-point function coefficient of an operator of charge, so there is q delta, capital Q, capital delta, minus q delta. In fact, should be q delta q, and this is minus little q delta of whatever. Okay. So I'm computing the three-point function of an operator of small charge with these vacuum states, with the corresponding charges. And what you find is that this three-point function coefficient was like q to the delta over 2. plus higher order corrections, with a universal coefficient, okay? What is remarkable is that this is true when these are all scalar primaries, but the same coefficient controls also the 3-point function when one of these guys has spin, in fact, all of them. All the excited states, all the 3-point function with the ground state and the excited ones are controlled by only 3 parameters. So you have cross information between, so you have a rich set of consistency condition for a 3-point function involving different classes. Now, last statement, what this is good for? Well, this is good for shining some light in specific limits of CFT. It's very much like, I would say, large N shines some light on large N H theories, okay? Maybe this already works, depends. It may work already well for Q equal to 5. I don't know. Okay, this gives you a criterion to, it's certainly an idealized limit, but it certainly carves out a subdomain of any conformal theory you can analyze. Notice that these large quantum numbers has nothing to do with the CFT. This is true in any conformal theory. The large N, we don't have a large N here. We have a large Q in the theory, which is a small N here. And the next thing it would be very nice to do is to apply this to spin. To really use these ideas to control states and correlators for operators with large spin and small charge. Sorry for taking up this time.